now we're going to talk about the factorization of density, which is very closely related to the ideas of conditional, joint, and marginal density, and tie some things together. So before we get into that, I want to quickly review this bit of notation. When I put this joint density and then I say of x, y, what I mean is at a particular value x and at a particular value y. So you can imagine here x and y are going to be, let's say this value is 2 and this value is m. If y is m, then this y is also m. This y is also referring to m, and this x is referring to 2. So this is a relationship between the numbers in these tables, right? So like this tells me like go to this particular table, the joint density table, which we have over here, and then the number that you get and the 2m row, which is this number. So this thing here is the 0.1 here. If you divide that by the number that you get if you go into the marginal table, which I'm not showing you, but it's going to be actually the sum of these 1, 2, 3, 4, 5 values. The number that you have there for so I'll just show you kind of what that table would look like. So if this is like you'll have sex and then I'll call it like fy. So m f, and then I think they're 0.5 and 0.5. So this fy of little y, if little y is m, then that says go to this table and look at the value at m. So that's the 0.5. So this would be like the 0.1, 0.5. That's going to be the same as if you go to this table, and then you go to so this table is actually not even really showing you the right thing. We're talking about the table that has sex also here. And so these are all going to be m. And then you have all the f's down here. Okay, so remember this is actually kind of like two tables glued together. So then if you go to this table over here and you get to the m for y, and then x is 2, that's this row here, that's this number, so 0.2. Okay, so that's what this notation means to be super, super concrete. Probably some of you are like, yeah, duh, dude, I get it. But I know that for a lot of people, the kind of functional notation is a little bit rusty. So what we mean here can be a little more unclear. So one way to look at it is like, okay, these two numbers, or the numbers in these tables are related in this way. Another way to think of this is like to construct this table, this kind of big table. All I need to do is for any particular value, like 2m, or here I have them backwards. For any particular value, all I need to do is go to these tables and get the values that correspond to this input, and then divide them, and I can construct this table from those two tables. Okay, so that is a bit of notation before we get into the factorization part. But now what we can say is if we can construct this table from these two tables, and in fact, you know that really this is just constructing it from this table, right? Because the marginal density also comes from the joint density. So it's really all coming from the joint density. But if this table is these two things put together in some way, then I can also just multiply on both sides by this number, and I get this. So another way to see this is like if I want to know the joint density, I can just, if I have the tables for the conditional and the marginal, I can get the value in the joint density table by just multiplying together certain values in the conditional and in the marginal density tables. And so this is the general kind of like formula or expression for the factorization of joint densities. So we call it factorization because we've expressed this number, which is a joint density, as the factor or as the product of two numbers. And when you have a number that's the product of two numbers, those two numbers that are getting multiplied together are called, you call them factors. So you can say that the original number factorizes, 10 is 5 times 2. So 5 and 2 are factors of 10. So we factorize the joint density into a conditional and a marginal density. Now, the thing about this is that you can take it further. And we're going to see this repeatedly throughout the course, that if you have multiple random variables, like not just x and y, but x, y, and z, or x, y, z, and w, and so on, you can still factorize that joint density in a very similar way. And there's a simple pattern here. So the pattern is you pick one variable. So in this case, I picked y. And then the next factor, you're conditioning on whatever's you've already picked, and you're adding another variable to be the thing that's like random, not conditioned on, and you're putting that here. So that goes on if you have 3 random variables. So here the first variable that I picked is z. And now the next factor is I have to condition on z, and I pick y to be the thing that is kind of the argument. And then the next factor I have to condition on everything that's over here, so y and z, and the next the random thing is x. So the reason this works is because it's just counting, right? So this joint density over here is like saying how many times does big X equal to X, little y, big Y is equal to little y, and big Z is equal to little z, relative to the total number of people in the population. That's what this is asking about, right? It's just like a proportion of times that this thing happens. Well, I could write that over here as this number is just this number right here. This big N is this little n here. And all I've done is I've multiplied by 1 twice. So let me make that clear. This number right here, whatever this count is divided by that count is just 1. And then whatever this count is divided by that count is also just 1. So these two things are clearly equal because it's just the same thing times 1 times 1. But now I've just kind of moved things around on the top and bottom of the fraction, so that now this thing right here is in fact this conditional density, because it's how many times does this whole joint event happen over in the subpopulation where defined by this, and this is how many times does this joint event happen in the subpopulation defined by that, and this is just how many times does z happen. So I can always factorize a joint density like this, and moreover, the order in which I kind of choose to do this factorization is not, unique. So I'll just write it here. I could have done this a different way. So I have the count of x, y, z over big N. Instead of dividing by the count of y comma z, I could have divided by the count of x comma z. And then here I would have an x comma z, and then a z and a z, which means that up here, if it's x, y, z divided by and then the count of x and z, the only thing that's free is the y. So this would have been f of y, and then this would have been x, and then this would have been x. And so it actually doesn't matter what order you factorize things in. You can always do it, and so you end up with multiple possible factorizations. So I could say this is also equal to the conditional density of z given y and x times the conditional density of y given x times the marginal density of x. Okay, and remember, if it's a little confusing, you can just fix x, y, and z, and then this is just one number is the product of 3 numbers. But what I'm showing, the way I'm writing it here, where x, y, and z are free, we're kind of saying, well, this function of x, y, and z factors into the product of these 3 functions, where that you can again think of a function as just get this particular number out of a table according to the inputs. And so to get back to my point here, you can factorize this in different orders. I could have put this like this, z and x. Here, let's say here. Okay, so hopefully you're seeing the pattern again. It's whatever marginal density you start with, that thing gets conditioned on, and then you introduce a new. So at first you pick one, right? And then you condition something else that you pick another thing, and you condition on the thing that you've already picked. And then all of that, you condition on that, and then you pick whatever's left over. So at each point you're introducing a new variable. So that's kind of the pattern. And I already talked about why that is the case in two different ways. One by looking at it as this kind of like count here, right? Where I'm just kind of multiplying by 1 at each step. And then another way of seeing this is like, okay, well, if this is the definition of the conditional density, then I just multiply by this thing over here. And then they're really all the same, it's equivalent. And then lastly, we can talk about this for discrete random variables where these counts make sense, but it's also the case for continuous random variables for the same reason, where if you're defining the conditional density as the ratio of the joint and the marginal, then just by moving the marginal over, you can see that this factorization occurs, and indeed that you can do this for multiple random variables as well.